This is Dr. Ali, and in this session, we want to solve hurdle1 using recursion method. So if you remember last session, we wrote this program that moved this robot from position 1 and 1 to position 113. We tried two different methods and we evaluate that our program is working correct. But in this session, we want to take actually a whole new paradigm for solving this problem. And this new paradigm is recursion. So let's see what is recursion. By the way, I have different recording regard to recursion, and we see lots of problems solving recursion. So if you don't understand what I'm saying here in the recursion, maybe you need to check those videos because I'm not starting recursion from scratch. This is just I assume that you guys know what its recursion is. But by the way, recursion is a technique for solving a large computational problem by repeatedly applying the same procedure to reduce it to successively smaller problems. So whenever we're dealing with the recursion, we need to, at each call of a function is called within itself, and at each call of the function, we face in a smaller and a smaller and a smaller the problem. And recursion refers to a programming technique in which a function calls itself either directly or indirectly. Recursion is a common mathematical and programming concept. A recursion procedure has two parts, one or more base cases and one a recursion steps. So the takeaway from this slide is that recursion is a technique. A function is called it's called in itself, and a recursion should have two parts, base case and recursive steps. So let's see how can we translate all of these to our problem here that we have. So what is the base case here? The base case is the smallest case that we know the answer, right? So we are looking for to stop this robot in the position 113. Basically, we are looking for the flag. So our base case could be whenever we see the flag, then we stop there, right? It could be our base case because we know that if you're in a cell, that there is a flag in that cell, so we know the solution is there. So that's our base case that we have. And what is the recursive part? If you look at the way that we solve, if the robot exists in the position 1 and 1, or they exist in position 1 and 3, what is the difference between position 1 and 1 and 1 and 1 and 3? Nothing, except that this position 1 and 3 is one step or passing one of these obstacles and get closer to that goal that we have, right? So we can, and remember, in recursive or recursion methods, we always need to bring down at each iteration or at each calling of the function, we need to face a smaller problem. So if you look at the robot here, the problem you're facing is passing all of these 6 obstacles to reach that position 113, right? But I'm saying if you want to break this problem into a smaller, we just need to move this robot from 1 and 1 position to 1 and 3. And if we do this correctly, so we can say by calling this method again, but this time calling it from this location, 1 and 3, we are basically one step closer to the goal, and we are facing a smaller problem because we want to reach from here to the goal. While in the previous step, we wanted to reach from here, 1 and 1 to 1. So that's how we can, that's basically the intuition for us to how we can attack this problem by solving it in a recursive manner. So let's see how can we change this code that we have to turn it to recursive. First, let me comment this out because this is for our method for solving it in the iteration manner. Okay. So now this one step, if we want to turn this one step to a recursive function, first we need to know what is the base case. And as we explained, base case is if we reach to that cell that has this flag. So I could easily say if at goal, just return. So this can be considered as a base. Basically, if we are at a cell that the flag exists, just return, do nothing, and stop there. We just basically reach our goal. But if not, what does that mean? If not, it means we are here, or we are here, or we are here, or here, and so on, right? So you are basically, we want to code it in a way that we will be exactly in a cell after this red obstacle. So we know that this part move from one desired location to another. So this one step, it goes from here to next step, next cell after this red obstacle. So if this one go to the next cell, I can easily here, after moving to the next cell, I can just call this function again, right? So basically this goes one step, right? And I can just say, call this function again inside this function, okay? And I don't think we need this return, but let's call it the return, and then we'll remove it to see if I'm correct or not. So let's run this. Oh, the thing is, we didn't call this function yet, so we need to here create one step. Let's run it. So awesome. Pass the first hurdle and keep doing it. There we go. We reach at our goal, and that finishes our program, right? So just one, I'm curious to know if we remove this return keyword dish, that still needs, I think, it work again, because this return doesn't do anything here, because this at this line 17, when this runs, the program finishes. We exiting this function, so we do not need to even return anything. But for just checking, let's see, am I right or not? Yeah, it seems it's working. Because basically this function doesn't need to return anything. There we go. So both of these scenarios work, and I hope that was clear. If you think some part of it is not, please leave your comment in the comment section below, so I will quickly try to answer the questions. And if you need more videos on different problem that you want to solve it in a recursive manner, please let me know so I can make more videos on those problems that you have. And stay tuned for more of this hurdle or more of this Reeborg's world problem that I will try to record in upcoming sessions. Have a great day, everyone.